the preservation of and increased access to the 92nd Street Y Humanities Audio Archives is generously funded by the National Endowment for the Humanities.
Good evening. Tonight we are to have the pleasure of hearing Professor Herman Mark, who will deliver the fourth lecture of this series on science in the modern world. Those of you who heard the lecture 2 weeks ago given by Professor Devens of Columbia were told about the very smallest things that we have knowledge of, namely the strange particles that come out of the nucleus of atoms. Today, Professor Mark will tell you about some of the largest units of matter, namely the giant molecules, polymers. And as you know from your booklets, the title of his lecture today is New Polymers, New Uses. Now, about Professor Mark, he knows who you are pretty well. He knows that this is an audience especially of laymen, laywomen. Professor Mark is the best known man in the world in the field of polymers. In 1944, I think it was, he founded the Institute of Polymer Research at the Polytechnic Institute of Brooklyn. You also know from your programs that he's Dean Emeritus of that institution. He is a member of many, many academies of science throughout the world. I shall not list them for you. It would take less time to list those academies of science throughout the world of which he is not a member. He is connected with the Weizmann Institute in Israel. He's a member of the National Academy of Sciences in our country. He was born in Vienna, received his doctorate in Vienna, was later professor in Vienna, and a man who should be introduced to you as really Mr. Polymer. You will not only hear him tonight, but he will also show you a few things. And it would be a grave mistake on my part to take any more time away from Professor Mark. It is my great pleasure to introduce him to you now.
It's a pleasure for me to be one of the speakers of this very well-known and famous series, and I would like to express also my appreciation to Mr. Wolf, who is here in the audience, for having made and actually making this series of lectures possible. Now, as Professor Szydlowski has told you, what I would like to report to you today, briefly, is some progress in the field of the very large molecules, materials which one usually calls organic high polymers or organic polymers. One calls them organic because they consist essentially of the four elements, carbon, hydrogen, oxygen, and nitrogen, like all organic matter does, with occasional presence of sulfur or of some other element, but by far the largest percentage of all of them is the carbon, hydrogen, oxygen, and nitrogen. One calls them polymers because it has been found in the course of the events that it's characteristic for these materials that the molecular weight of the individual molecules is very large. You know that molecular weight of those organic substances with which we have to do every day, like sugar or soap or gasoline or vinegar, is between 50 and 100 or 150 or something of this order of magnitude. On the other hand, the molecular weight of these organic polymers is not 50, but it's 50,000, 1,000 times larger, sometimes even larger than that. Sometimes it goes into the millions. So they're very large, 1,000 times larger than the normal organic substances. Now they have played a very important role in the form of their natural representatives. In fact, we all consist of them. Proteins are organic polymers. Cellulose is an organic polymer. Everything which grows on this earth consists substantially of these organic polymeric materials. All our clothing did consist of them. All cotton, all wool, all silk, all leather, all fur is made of molecules of this type. If you pull out a cellulose molecule from your handkerchief, you would find that it has a molecular weight of about 120,000. And the same thing is true with a molecule in my hair. So these materials have served mankind throughout the development of all civilizations. In fact, there wouldn't be any civilization if they would not exist and if they would not be used. All wood which is used for housing, all wood which is used for shipbuilding, the sails on a ship, everything which we have used throughout the centuries for transportation, for art. Every violin is made of nothing but of such organic polymers, partly the wood, partly the lacquer, partly, of course, the guts. So they have accompanied us throughout the development of the human race. And while they have been used so extensively, one didn't know anything about their structure. One didn't know their composition, and one didn't know anything about their structure. So all the utilization, all the application was entirely on an empirical basis. It was in every individual case an art. And as you know, a very highly developed art. Paper making in China and in Egypt and now was an art for very many centuries. Textile industry was an art, and to a certain extent still is an art. It wasn't until the beginning of this century that the chemists felt that their tools, their hardware, the arsenal of their experimental methods was sufficiently developed in order to analyze the structure of these materials. Even when the first attempts were initiated, just about 60 or 65 years ago, it took a long time, it took 2 decades, until actually the elements of their structure were discovered. First, it was found that these molecules are very large. Determinations of the molecular weight led to the conviction that we are dealing here, in the case of the proteins, in the case of starch, of cellulose, of rubber, and of all of those useful things, with very large molecules. Now then the next question, of course, was, is there anything common in the shape of these molecules? Because as long as a molecule is small, like water or like gasoline, nobody will be very much excited about its shape. Well, it'll have the shape of a sphere, maybe it has the shape of an ellipsoid, or maybe it has the shape of a disk, but so what? It can't matter very much. But if a molecule consists of 20,000 atoms, then, of course, the question is extremely important. How are these many atoms combined? Do they form a cluster? Or are they a chain? Or are they a big flat disk? Or are they a star? Or do they look like a Christmas tree? How are they arranged? So that the first step was they are large. And the next step was that they are all essentially chain-like in their character. In order to establish these two fundamental facts, it was necessary not to use strictly chemical methods, but to use methods which were taken over from physics or from physical chemistry. And I think it is characteristic for the entire development of this branch of chemistry, a branch of chemistry which deals with the very large molecules, that we have to borrow permanently from our colleagues in the physics department new tools and new experimental methods to get more and more information about these large molecules. The molecular weight of these big molecules, the first important information, was essentially established with the aid of the ultracentrifuge, an instrument where one has a top which spins around very, very fast. In this container, in this little container, is a solution, and a solution of this macromolecular substance. And then, because of the very high gravitational field or centrifugal field, one gets a sedimentation phenomenon, and this sedimentation phenomenon permits the calculation of the molecular weight. And since I see up there the word Einstein, I may remind you that actually Einstein was the man who derived the law with the aid of which the experiments of this type are evaluated. The fact that all these big molecules consist of chains was established by another important physical method, namely by the diffraction of X-rays from these materials. From the enumeration of them, you realize that they are all substantially solid substances, and the X-ray diffraction method permits us to establish in a solid crystalline material the shape of its individual particles. And I want to show you in the first slide just a few of these X-ray diagrams as they have been obtained from polymeric materials. Down here, you see an X-ray diagram from a sugar crystal, a simple sugar crystal. And there you can see there's a very large number of sharp points, and these points in their position and their intensity, they reflect the position of the individual sugar molecules in the crystal. That's the sense of an X-ray diagram. The sense of any scattering experiment is that the distribution of the scattered radiation on a photographic plate or on a screen reflects the distribution of the scattering particles, that is, the atoms and the molecules in the irradiated sample. And the high degree of order here actually reflects a high degree of order in the sugar crystal. And here you have now a large number of X-ray diagrams from cellulose and from rubber and from starch and from several proteins, and for that matter also from synthetic polymers. And there you can see that the degree of order is not as high as it is here, but there's a definite existence, a definite presence of intense and relatively sharp diffraction points, which show that there is an order, a certain degree of order, and from the position of these points it was possible to calculate the shape of the molecules, and to what one arrives is that all these materials essentially have the shape of long chains. I think we can have the light again. We don't need the slides until a little bit later. So a molecule of cellulose is such a chain where each individual bead represents one unit, a sugar molecule, only that this would have 70 individual sugar molecules, whereas cellulose has 700 or 1500. So they are very long. And of course, because of their lengths and because of the flexibility of the bonds in an organic molecule, they are also flexible. They can be rolled up and they can deform. They can either be randomly coiled or they can be extended, and for that matter, the whole phenomenon of muscle contraction is nothing but a change of protein molecules from the extended state into the contracted state. The elasticity of rubber is nothing but a change of the rubber molecules from the extended state into the contracted state. So all the mechanical properties of these materials, the elasticity, they all have to do, and in fact can, to a certain extent quantitatively, explained and also pre-calculated if necessary, from the known chain structure of very large organic molecular systems. Now, as soon as there was an idea about these structural characteristics, chemists felt that it was time to start synthesizing molecules of this type. You see, it's a tradition in chemistry, as you know. A chemist works on a natural substance, let us say he works on penicillin or he works on insulin or on something of this type. And as soon as, on the basis of his analytical work, he has a certain idea about the structure of the material of his interest, he starts synthesizing it or similar things. And eventually, the last word about the structure of a natural substance, whether that is indigo or whether that's penicillin or whether that's any other natural material like cellulose or rubber, is the success in making it synthetically. Because then you see the two arms joined, then analysis and synthesis give us a completely satisfactory answer as to what we have to do with. And so it was here. It was possible to synthesize completely identical materials for simpler types of organic natural polymers. It was not yet possible, but it will be someday, to synthesize even more complicated species such as proteins or maybe certain cellulose materials. But once the principle of long chains was established, the interest of the chemists, academic and applied, that it not only centered on verifying their analytical results by synthesis, but also obviously centered on the question, well, can we make long-chain molecules of other substances, other materials than those which exist in nature? And if we can, let's do it and find out what kind of properties they have. And this, as you know, has led to the now rather elaborate and well-developed chemistry of synthetic polymers. Chemistry of synthetic polymers, which have nothing to do with the natural materials as far as their composition goes, but which use the concept of high molecular weight and of chain structure. In nature, there doesn't exist anything like nylon. In nature, there doesn't exist anything like polyethylene or all the many other plastic materials which you are using every day in the kitchen, in the bathroom, and everywhere. There doesn't exist in nature any material out of which a brush or a comb is made today, or for that matter, most of our clothing is made, or a lot of our clothing is made. Nevertheless, they are prepared and synthesized according to a recipe which we have extracted, or which chemists have extracted from nature. And the recipe is make the molecules very large and make them chain-like. Now, in order to do that, in fact, not just planning it, it was necessary to develop first a science and later a technology of chemical reactions which permit to tie a very large number of molecules together into a long chain. Such reactions were completely unknown before, let us say, 1920 or 1925. The classical organic chemists of the last century, they have never occupied themselves with such problems. They occupy themselves with the problem, how can I get together a new dye stuff? How can I get together a new pharmaceutical material, molecules which have molecular weights of 300 or 350 or something like that? In other words, it was a new venture. It was necessary to start on new types of chemical reactions which would form long chains. And evidently, if I want to make a long chain, the most logical reaction will be one which repeats itself always in rapid sequence and which therefore is called a chain reaction. So in the early 20s, the science and technology of chain reactions was developed. In fact, the burning of a flame is a chain reaction. Only in the burning of a flame, the temperature is so high that the reaction product actually disappears. The polymerization of ethylene or of styrene or of nylon is also a chain reaction. But this reaction is carried out at a temperature which is so low that the chain remains in our hands, and in fact the chain is the important and valuable ultimate product. So in the 1930s, the science and technology of chain reactions, organic chain reactions, was initiated, and it was particularly successful because of the fact that the raw materials which are needed in order to carry out such reactions are very inexpensive and very plentifully available from the oil industry. You see, it was a kind of a lucky coincidence, maybe it wasn't a coincidence anyway, it was a fortunate fact that while the chemists were looking for materials which they could string out in such long molecules, those materials actually were byproducts of every oil refinery. So that soon oil refineries, which originally, of course, were designed to make gasoline and lube oil, found that their rejects, the gaseous fragments of the cracking of crude, actually were molecules which could be made into long chains, or as one calls it, which could be polymerized. In fact, just to give you a few examples, ethylene. Ethylene is a gas. It's a gas like natural gas. Its molecular weight is about 30. Ethylene costs 2 cents a pound. It can be polymerized. In other words, out of ethylene, the small molecule, one of these beads, one can, in a very simple process, build up very, very long chains, which consist of 5,000, 6,000, 7,000 individual ethylene molecules. And these chains then are a plastic material, which you all know very well, the polyethylene. It's the thing which you get back with your laundry or with your suits when you send them to the cleaner, and it's the thing which you buy everywhere in all Woolworth stores, and all combs and everything almost consists of plastic materials of this type. Now, the polymerization process itself is not very expensive. May cost 5 cents a pound. So that actually the polymer, the raw polymer, the raw waxy or plastic resinous material which comes out of the reaction after some purification may cost altogether maybe 10 cents, 8 or 10 cents a pound. And that is the reason, you see, why oil pails and almost everything which we use today is made of these plastic materials, because they're much cheaper than metals, they're much lighter than metals, they're easier, they don't corrode. And so they have invaded, you know, our life in terms of very many practical applications. The same thing, of course, is true in the rubber industry. Rubber itself is a polymeric material, natural rubber. And when its structure was analyzed, one found that it consists of a certain unit, and that the chains of natural rubber, that they contain some 800 such units. So the chemists took that unit, or a very similar unit, which again is a product or a byproduct of oil refining, and made long chains out of them. And then sure enough, these long chains have either exactly the properties of natural rubber or very similar properties, and in certain cases even better properties in terms of stability, in terms of resistance against hot oil, resistance against ozone, and so on. And all the tires which you are using, and all the shoe soles, and everything rubbery which one is using today, consists essentially of these synthetic elastomers. You know, before the war, around 1940, the import of natural rubber was about 800,000 tons into this country. And of course, there was no other material, there was no synthetic rubber in 1940, not in this country, there was some in Germany. Today, the consumption of elastomeric materials is about 2.5 million tons, 3 times. Yet all the natural rubber which we import today is only 300,000 tons. So the import of natural rubber has gone down to 1/3 of what it was, and the consumption has gone down to 3 times of what it was. So that actually what we are using now is about 12 or 13% of all the elastomeric materials which are used today are natural rubber. And in this we wouldn't buy if we wouldn't want to give some foreign aid, really, in these terms to those countries where this material is made, and even that won't last very long because the price of the synthetic materials goes so far down that one really can't afford anymore to use natural rubber. So it's the plastics industry which has greatly profited from the advent of these materials based on our understanding of their structure and on our capacity to synthesize them and similar materials. And the rubber industry has greatly profited. Another industry which has greatly profited, as you know very well, is the textile industry. It is, of course, possible to make textiles, that is fibers, out of these polymeric materials. And again, after some early attempts, which were just forerunners of what was to come, the old rayon, the old Kunstseide, which you all remember, which wasn't very good. Now we have a whole spectrum of synthetic fibers, which together with the natural fibers, or alone, depending upon for what they're used, as you know, give us entirely different choice in fabric behavior and in fabric construction as compared with what we had before. If today we would have to go back to the natural fibers alone, everybody would be very disappointed, not only as far as apparel is concerned. Certainly the ladies wouldn't like to have cotton or stockings and such things. And, but it always goes much further than that. It goes to carpeting and to upholstery and to the entire field of textile industry. And again, one of the main reasons why the synthetic materials were so successful in invading this industry and in filling out a lot of holes between the natural substances was because of their properties and also because of their price. As you know, you can buy today a lot of things which you couldn't buy before at a relatively low price. The industry of coatings is another one, but I don't want to talk about too many details. I think we can say that the three big industries, textile, rubber, and plastics, they are built today to a very large extent on these synthetic long chain molecules, where the raw materials are taken from the oil industry and where there has been built up a substantial science and technology as to how to string up these small molecules into long chains. So that's where we stand today. And that raises the question, well, what will the future bring? What can we expect in the next 5 or 10 years to happen in this field? After all, as you know, in any science, one permanently is interested in forecasting. We are not only interested in what we have today, we are interested in reviewing our fundamental knowledge, reviewing the availability of raw materials, and then forecasting as to what else, what kind of new things could we do with these raw materials and with whatever art we have developed in either smashing atoms into smaller and smaller bits, as it was discussed the last time, or in building up larger and larger molecules from those given elementary available materials. And there I would like to mention two things, I think, where we can expect in the not too distant future very substantial additional improvements, or let us say additional progress. One is that everything which we are getting today, all the rubbers, all the synthetic rubbers, and all the rubber goods, and all the textiles, and all the plastic materials, will still be available at a much lower price, ultimate selling price in the department stores or wherever you buy them, than today. And of course, that'll be nice, that'll be convenient. Why? Well, first, the raw materials, this ethylene and propylene and the other simple substances of this type are becoming less and less expensive because the units which are now the refining units, the units of the refineries are always going up. You know, a large refinery today makes about 10 million tons of, or refines 10 million tons of crude. There are already now being built refineries which refine 30 million tons of crude or 40 million tons of crude a year. Well, evidently, that not only makes the gasoline or the fuel oil and the lube oil less expensive, although we might not actually feel that because of the taxes, but it also makes the byproducts less expensive, and therefore the raw materials for those polymerization units which are now built around every refinery. So that's one thing. Second is that the technology of the polymerization process is being better and better developed, and that keeps another cent off the price of the polymeric material, the raw polymer. And then, and this is probably the most important thing, the methods of manufacturing the ultimate goods are being simplified and are becoming less and less expensive. The spinning of fibers, the weaving of cloth, the casting of films, the injection molding, other molding processes, temperatures are higher temperatures are used, and therefore one can extrude faster. Nylon was spun with 40 miles an hour 10 years ago. Today it's spun with 80 miles an hour. Probably in a few years it'll be spun with 100 miles an hour. Because why? Well, because one can make the material at a more homogeneous character, and one has better equipment, one uses higher pressures, and whatnot. Just like steel, no steel production. Why is steel production permanently improving? There's no change, there's not much change anymore in the composition of the steels, but there's a lot of change in the manufacturing methods. So I think this is one important thing. We will have all these materials less expensive. But the other important thing is that we will have a whole number of entirely new materials with properties which have not yet been obtained in large-scale production today. And I want to show you a few of them. And before I do that, however, you will ask me, well, why is that? What enables us today to enter new uses, and that's why the lecture was called New Polymers, New Uses. Why can we make today new polymers which will permit new uses? Why couldn't we do that 10 years ago or 20 years ago? What has happened? Well, what has happened is that a new idea, a new concept was first dreamed up or first conceived and then later materialized by experimental facts. And this new concept, as all fundamental ideas, is very simple. And it is the following. As I told you, the normal organic macromolecules like polyethylene consists of a large number of ethylene molecules. Ethylene is CH2, two small units. And the polyethylene, the thing which you have in your brush handle, just consists of 10,000 CH2, 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 a very, very long chain of these small groups. And they are all connected by single bonds between the carbon atoms. So it's a very, very long chain, substantially based on single bonds between carbon atoms. Now, organic chemistry, one of the fundamental laws of organic chemistry is that the single bond, a sequence of single bonds in an organic molecule, is a flexible arrangement. It's like a large number of joints, like this chain here. A long chain of CH2 groups is like this one. That's why it is soft, that's why it is elastic, that's why it is moldable. And that's also why it has a low melting point. And that is also why it is not as rigid and stiff as a metal. And that is also the reason why eventually it dissolves in hot oil. So the idea came up, if I want a new type of macromolecules, if I want a new type of chains, which will be much higher melting, which will be much more rigid, and which will not dissolve in anything, which will be much more chemically resistant, I should not make it out of individual single bonds, I should make it out of rings. So some 10 years ago, a few chemists said, well, let's try that out. Find out what would happen if instead of building up a chain of CH2, CH2, CH2 as the polyethylene, you see, polyethylene is a very long chain of this type with very many single carbon-carbon bonds in a line. We know those things. We know what they can do, and we use them all the time. And then people said, let's now instead build up a chain which has a kind of a honeycomb character. Namely, let's put 1,000 rings of this type, benzene rings, together in a long chain. And let's find out what will the properties now be. Here you see we don't have this flexibility. Here we have something which is a stiff molecular rod. We have something which is stiffened by a honeycomb structure, but it is a molecular honeycomb. It's not a macroscopic man-made honeycomb. It's a molecular honeycomb where the individual rings stiffen the chain. And on the next slide, I'll show you a number of examples of molecules of this type. Maybe, could we push it down a little bit? Well, that's all right. If you can't do it, never mind. No, down. I thought you could possibly put it down a little bit. Yeah, thanks a lot. Thank you very much. Because I wanted to show you this one. You see, this is a very simple molecule of this type. It's a benzene ring, and a bond, and a benzene ring, and a bond, and a benzene ring, and so on and so on. And this is another one a little bit more complicated, and this is another one still a little bit more complicated. There we just have naphthalene rings linked together, and they are even more complicated. But these ones here, you see, they are interesting because they are also based on very simple and available base molecules, namely on benzene. Well, benzene is gasoline, and certainly is available. So the idea came up, how about polymerizing benzene? Let's take benzene and find out whether we can make a polymer of it. And sure enough, after a while, one found methods to build up very long chains of rings, and specifically of benzene, of phenanthrene, of naphthalene, and of these more complicated rings. Thank you very much. I think we can have the lights again. And then these chains, they fulfilled essentially the expectation. Namely, the materials which were made of them, films, fibers, other materials, had much higher melting points than those which we know from the flexible macromolecules of this type. So today, you see, there exists a classical polymer chemistry which deals with molecules of this type, and there may be all kind of substituents, and there may be all kind of oxygens in between, and nitrogen and whatnot. And that is what we use today in textile industry, in paper industry, and in plastics industry, and in rubber industry. And now is being gradually developed the new macromolecular chemistry, which is based on chains of this type. And again, they may have substituents and may be more complicated and all kind of things. But all of them have much higher melting points, are much harder, are much more resistant against dissolution and against chemical action than these ones. I'll show you a few of them. I have here a film. Quite a thin film. In fact, it's quite a good-looking film. As you can see, it's yellow, very thin. It's about a mil thick. And you can really abuse this film. You can really do. So maybe you want to play around a little bit. It's much stronger than any existing film which you have on the market. Yeah, you try. Well, you see, mylar is a material which belongs to this class. This film is made from a material which belongs to this class. Yeah, give it around. Now, the really interesting part is not so much its increased strength, but its increased heat resistance. You see, I have a hot plate here, and I can wrap this hot plate in this film. And I can keep it here for an hour, any length of time, in fact. And it doesn't melt, and it doesn't decompose, and it is unaffected. Actually, if you measure the melting point of this film, as it was done, of course, it's 800 degrees centigrade. It melts about 200 degrees higher than aluminum. You can have it you can have it red hot, as you have it here, and it doesn't melt. Now you can see what that means. It means that we have insulating materials today, wire coatings if you want, which can be used at temperatures of 600-700 degrees centigrade, which means that one can run today an electromotor at 400 or 500 degrees centigrade. Now you know that if we can do that, then one can push through that motor a much higher current density, and therefore the size and the weight of the motor becomes much smaller. So today, in many servo mechanisms, I can leave that. You see, in my class, I usually cook a cup of coffee through that film. I put a beaker of water on it and make coffee in front of the boys or girls. They like it. And this is a material, specifically a material, in which there are always two, well, I'll show you what it is. It is this material. In other words, we have a single bond, then we have three condensed rings, and then we have again a single bond. And this kind of structure, whether it is this or whether it's something similar, always leads us into this field of temperature resistance. As I said, this is already being now used in the building of servo mechanisms. If you want to have a very light but nevertheless strong electromotor, you insulate it with this material. It's also used in something which will interest you, namely in the construction of the SSTs, you know, these big supersonic transport planes which are now being built and which are already in an experimental stage. These planes, they fly at about 70,000 feet with some 2,000 miles an hour. And when they come down, when they enter the atmosphere, they heat up. They have a little bit of a re-entry problem. When they are slowed down, there's tremendous friction and they heat up. So that the surface of these planes warms up to about 300 degrees centigrade. Not for a very long time, maybe for 20 minutes or 25 minutes, but nevertheless long enough so that aluminum wouldn't stand it. It would lose so much strength that the plane would disintegrate. So therefore, these planes are insulated by insulating units of this type. And there you have here a plate of steel or of titanium, whatever it is, and then there's a honeycomb structure of this film. Kapton is the name of this film. And then at the end there's a fabric of fibers made of Kapton. And with this it is glued on the aluminum wing of the actual plane. And this is mechanically very strong and gives all the insulation which is needed to keep the plane at a normal temperature, whereas the surface is 300 degrees centigrade. And this material can take it. It doesn't lose any strength, even though the shearing forces, of course, on it are very large. Now, again, I would like to say that this is not just a substance. This is a representative of a big family. It's just as much a representative of a big family as one synthetic rubber is a representative of a very large number of possible and existing synthetic rubbers. All right, so after that was realized, then, of course, the next question was, well, if more and more rings give us higher and higher resistance against elevated temperatures, what about going a step further? How about making a molecule which looks like this? In other words, how about keeping on condensing rings together? Now then, molecules you see of this type are called ladder molecules because they have the shape of a ladder. We have two beams, and between those beams we have frequent bonds. How about synthesizing long chains which have still more cyclic elements than this Kapton has? And again, it can be done. If one does that, one gets a very large number of double bonds in what is called conjugation in local, in the immediate neighborhood, and therefore the color of these materials becomes dark. In fact, molecules of this type, long molecules of this type, are really, as you can see, a kind of a linearized graphite. If you would take this structure and extend it in 2 dimensions, you would get the structure of graphite. But if you build up something like that in 1 dimension, you have a linearized graphite, or you have a new version of carbon. You see, we know from nature, we know 2 types of carbon. One is diamond, which is the 3-dimensional lattice, and the other one is graphite, which is the 2-dimensional carbon. We have now made the monodimensional carbon, filamentous if you want to. And sure enough, this looks like carbon, it's black. And I have here filaments of this type. Here is a filament of this type that has this substantially the structure which I have up there. And these filaments are quite strong. You can tear them, of course, but they have a fair strength. Well, they're about as strong as cotton. A cotton yarn would have about the same strength as these filaments. But the interesting thing now is, again, not so much the mechanical properties, but is the thermal properties. Because these filaments, they can be heated to much higher temperatures. You see, I can take that and put it in this burner and have it really warm. And yet, you see, I have it under tension, and it doesn't break. I can keep it here for, I don't know what, for an hour or so, and it won't break. And after this, it hasn't even changed its strength. In fact, once it has cooled down, one doesn't even know where it has been heated. Now, if you have filaments, of course, you also can make fabrics. Maybe you want to You also can make fabrics, and I have such a fabric here. And these fabrics, of course, have the same properties as the filaments. They are strong, and I don't want to say that they are extravagantly strong. Their strength is not their main property. Their main property is their high temperature resistance. And here is such a fabric, you see. It's quite a flexible fabric, as you can see, reasonably strong. Oops, sorry. But again, what is interesting is the thermal resistivity, the fact that you can heat this fabric can make it nice and warm, you see. And nothing happens to it for any length of time, practically. Now, not only do these structures stand temperatures of about 1,000 or 1,200 degrees. They also stand temperatures of 4,000 and 5,000 degrees. And this is, of course, their value. What is being done, for instance, is the following. You take, this fabric is being cut in ribbons of this width. Then these ribbons are run through a thermosetting resin, and they are imbibed with a thermosetting resin. Then they are wound around a mandrel, 1 ply, 2 plies. Then the resin is set, and then the whole thing is carbonized. And then you get pipes, you see? Pipes of this type. And these pipes really are nothing but carbon. There's a little bit hydrogen, very little hydrogen in it. And these pipes, you can hear that they are very hard. You have seen that they never melt. And of course, being carbon, they are not attacked by any chemical ingredients. And they are used, for instance, in atomic energy plants to pump the liquid sodium around, or they are used in plasma physics for the walls of containers which can stand 4,000 degrees centigrade temperatures of this type. Every metal would be completely, not only would be molten, most metals would actually vaporize under such conditions. Now, if one can make a fabric of the kind you have there in your hands, one can also make a felt, and actually such felts are being made from these materials. I have here a piece of such a felt here. And then felts of this type, by the way, this material is called pluton. Felts of this type are also soaked in a thermosetting resin, and then they are pressed on each other, maybe 4 or 5. Then the resin is thermoset, and then the whole structure is carbonized. And that gives the heat shields. That's the way the heat shields are made, for the returning space vehicles. You know how they look. If this is a space capsule, then it has here such a heat shield. And the heat shield is made out of this material after it has been condensed with a resin, and the resin has been carbonized. Now, this shield here, upon the first impact in the atmosphere, reaches a temperature of 5,000 degrees centigrade or something like that. Every metal would not only melt but vaporize. But here, this very slowly vaporizes. The heat of vaporization of carbon is very high. So what happens is that carbon atoms are actually streaming away here, you see, on both sides. And the heat of vaporization of carbon, which is taken out of the system, cools it. And this is what one calls ablation. The resin slowly evaporates while it is cooling the metal layer underneath. Usually these heat shields are about 2 inches thick, and that after the return of the vehicle, half of the shield is kind of burned off. Of course, this peak temperature of 5,000 degrees centigrade only lasts for a few seconds, and then it goes down to 4,000, goes down to 3,000, and so on. But it's just this first shock. It's just this first heat shock which has to be taken care of, and no other material can do it except these highly condensed polymeric materials, which consist of chains which in turn are built up from rings. Now, this is, of course, somewhat extravagant application, but you can see to what it all will lead once these things are developed and once they become available. it'll lead to new materials for building construction. If once pipes of this type will be available, nobody is going to use any metal pipes anymore because they are much lighter and they are easy to handle and they don't corrode and whatnot. As one can make a fabric and a felt, one can also make a foam. And what is being now done, these Pluton-type materials are formed into bricks of this size, maybe 2 inches thick. And these bricks are now being experimentally used in buildings. And they have the advantages, see, they never burn, they never soften, they're very light, they're completely non-attacked by fumes or by any other things, and they have a rather considerable strength, as you have seen. So you see, this is what is being done now in the field. First, everything we have now must become cheaper and better on the basis of standard progress in existing technology. But beyond that, there's a big new field of new types of macromolecules, of polymeric chains which consist of rings. And they lead us into entirely different property areas and therefore also into new uses. Well, thank you very much.
Thanks for listening. For more information on the 92nd Street Y, New York, and all of our programs, please visit us at 92ny.org.